Hello everyone and welcome back to MrMiers Math Channel. Today in Chapter 10, we're actually going to start getting into the probability portion of this chapter. And mainly what we're going to talk about is counting principles and how to count things, because that's a very important part of figuring out probability, figuring out the number of different ways various events can happen. So today in Chapter 10, Day 5, we're going to talk about the fundamental counting principle and permutations. So let's get started. First, we're going to start with this question. How many lunch specials can you choose from if you can choose chicken, pasta, or fish as a main dish and soup or salad as a side dish? Of course, a lot of assumptions are going to be made here. One of the assumptions is that you can only get one of each, and you must get one main dish and one side dish. So one way to answer this question is to use a tree diagram. So that's what we're going to do first. All right, so first we have stemming out all the different types of main dishes we can have. We can have chicken, we can have pasta, and we can have fish. And based on each one of those, we can have two different side dishes. All right, so we could choose chicken, and then we could also choose soup and salad. We could choose pasta, and we could still choose soup or salad. And then we could choose fish and still choose soup or salad. So based on this, we can see that there's 6 different possibilities of what we could choose for our lunch specials. We could choose chicken and soup, chicken and salad, pizza, soup, pizza, salad, fish, soup, fish, salad. All right, so that's 6 different possibilities. All right, one way to get that 6 is there's 3 choices for our main dish, and then there's 2 choices for a side. And obviously 3 times 6 then would give us that 3 times 2 would give us those 6 different possibilities for what we could choose as our lunch special. All right, so that's just an introduction into how we can figure out what the counting principle is. All right, so by definition, the fundamental counting principle for 2 events states if one event can occur in m different ways and another event can occur in n different ways, then the number of ways that both of the events can occur is m times n. Okay, if 3 events are happening, then we have the number of ways that the first event can happen times the number of ways the second event can happen times the number of ways that the third event can happen. And of course, the counting principle also extends to 4 or more events as well. All right, so in example 1, let's say we're ordering a case for our MP3 player. You can choose any 30 colors for the main shell, any 32 colors for the protective band, and any 200 decals for the cover screen. So how many different cases are possible? Using the fundamental counting principle, this is pretty simple. We have 30 different choices for the main shell, then we have 32 different choices for the colors of the protective band, and then we have 200 different choices for the decals on our cover screen. All right, if we multiply these different events, we would get 192,000 different options or different combinations that are possible here. Awesome. So in example 2, you're choosing a password that has 4 letters followed by 2 digits. So an example would be NCWJ37. Now there's assumptions that we're making in here. One assumption is that we can only choose like uppercase letters, no lowercase letters, no symbols, no spaces. And it has to be 4 letters followed by 2 digits. Okay, so we already know that this password is going to contain, because it's one of the requirements for this question, 6 letters. Or sorry, 6 characters. All right, the first 4 of which are going to be letters, the second 2 are going to be digits. All right, in order to figure out the number of different passwords that are possible, if letters and digits can be repeated, we have to figure out how many letters there are in the alphabet, which is 26. And if we choose a letter, can we choose it again? And this says letters and digits can be repeated. So even if we choose N, we could choose it again for our password. So that means we have 26 options for the second character, 26 options for the third character, and then 26 options for the fourth character. For the last 2 characters in this password, that's going to be 2 digits. All right, then we have to figure out how many digits do we have to choose from. Well, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 that we can choose from for each one of these spots in our password. So, right, so that's 10 options. for the first digit, followed by another 10 options for the second digit. If we multiply all those together, we get 45,697,600 different passwords that are possible with these parameters. That's pretty crazy because most websites require at least 6 characters, and they also have a bunch of other requirements that you have in the password, like symbols, lowercase letters, uppercase letters, digits, and things like that. So this is a very minimal amount of passwords that are possible with only 6 characters. In part B, how many passwords are possible if letters and digits cannot be repeated? So given these parameters, we still have 6 characters that we're choosing. The first 4 is still letters. Okay, so we have 26 options for the first letter that we choose. But then once we choose that letter, it says the letters and digits cannot be repeated, so we can't choose it again. So if we chose N, we can't choose N again for the second character, which leaves 1 less possibility. So that means we have 25 possibilities for the second character. And then if we choose C, we can't choose C again. So we can't choose N or C now. So then we have 24 options for the third character, followed by 23 options for the fourth character. And then for the digits, it's the same. We have 10 options for the first digit, but once we choose that digit, we can't choose it again. So that means we only have 9 digits or 9 options available for the last character. All right, so this would give us 32,292,000 different passwords that are possible. So we'll see that when things cannot be repeated, there's a less amount of passwords that are possible. So the more and more restrictions that are required, the less possible passwords. The more open it is, the more possible passwords there are. Of course, a lot of organizations and a lot of websites require some restrictions, like you must have a certain character, or you must have, a digit or lowercase letter or uppercase letter or something of the sort. But they do that actually to create more possibilities for the passwords. Okay, so if we had like 26 options for different letters, that's 26 uppercase letters, 26 lowercase letters that are possible. And then also if you can include digits and maybe like some special characters, that gives us a lot of different possibilities for what we could choose for each one of the characters. So that's crazy. All right, let's go to the next one. Now let's talk about PIN numbers. All right, we're choosing a personal identification number for our ATM card, and let's say our PIN has 4 digits. We want to figure out how many PINs are possible if digits can be repeated. So the amount of digits we have to choose from is the same. We have 10 digits. Okay, so that's 10 possibilities for the first character in our PIN. And then if they can be repeated, we still have 10 options for the second, the third, and the fourth character. All right, this would give us 10,000 different possibilities for what we could choose for our PIN for the ATM card. And now let's see what happens when the digits cannot be repeated. Okay, we'd have 10 options for the first digit in our PIN, 9 options for the second digit, 8 options for the third digit, and then 7 options for the fourth digit. All right, this would give us 5,040 different possible PINs that we could choose. So right there we can see, man, it almost cut in half. Okay, we have only half of the amount of PINs available just because we couldn't repeat some of the characters. So that's crazy. All right, let's get to the next one. Now we're going to talk about permutations. So we talked about the fundamental counting principle. Now permutations is something a little bit different. All right, so let's start with this. An ordering of a set of objects is a permutation of objects. Okay, by the fundamental counting principle, there are 3 times 2 times 1, or 6 permutations of 3 objects. For example, here they are listed below. We have 6 permutations of the letters A, B, and C. A, B, and C are each objects, and a permutation is something in which order matters. Okay, so notice we can't repeat these things because it's an object. It's like we're placing it. All right, so if we look at all the different orders for these 3 letters, we'll see that there's 6 possible permutations of these 3 objects. All right, A could be first in the lineup, and then B could be either second or third. B could be first, and then A second or third, and then C could be first, and A second or third. All right, one way we could figure this out, or one way we could do this mathematically without actually drawing or writing all the different possible outcomes, is we have three options for the first object. Once we choose that object, now we only have two options for the second object. And then once we choose that object, we only have one remaining object to place. So this would give us our 6 permutations. All right, this expression 3 times 2 times 1 can be written as what's called 3 factorial. Okay, so the factorial symbol is that exclamation point, and it's read as 3 factorial. So we're going to be using factorials often when we're talking about permutations. All right, so here is one of the definitions for a permutation of n objects. All right, the number of permutations of n distinct or different objects is n factorial. All right, so if we have n objects, we could figure out the number of different ways to arrange those n objects by n times n minus 1 times n minus 2, and so on, all the way until we get down to 1. So 4 factorial is just 4 times 3 times 2 times 1, which would be the ways to arrange 4 objects. 5 factorial would be the amount of ways we could arrange 5 objects, and so on. So 0 factorial is a special case. 0 factorial equals 1. Basically, the way I like to say this is there's one way to arrange 0 objects. We just do nothing. All right, so let's try these. Try these in your calculator. In order to type this into your calculator, instead of writing it out as 3 times 2 times 1, or 7 times 6 times 5, and so on, all the way until we get down to 1, is there is actually a factorial button in our calculator. And I'm going to show you that in just a couple seconds. So for 3 factorial, we get 6, like we demonstrated before. And for 7 factorial, we get 5,040, which is something that we got in a previous example. Now, once again, I said I was going to show you how to type this into your calculator on the following slide. You'll see that if you have like a TI-84, TI-83, or those types of calculators, you can hit math, which is right there on the calculator, then probability in the options that it displays, and then hit 4, or just scroll down and press enter on that exclamation point, which is our factorial. On these TI-30XS calculators, you can hit the PRB button, and then after that, you just move to the exclamation point and hit enter. So it's pretty simple. All right, now let's get into some examples where we can demonstrate the permutations that we have. So an example, 8 skiers are competing in moguls. In how many different orders can the skiers finish the competition? If we have 8 skiers, there's 8 different places that are available. All right, so first we have 8 different people that could get first in that competition. And then once that person crosses the finish line, there's 7 remaining that could get second. Once they cross the finish line, 6 remaining, 5, 4, 3, 2, 1. So we could see that we could have typed 8 factorial in to figure out the number of orders the skiers could finish the competition. Now, if we did that, we would get about 40,320. Which is crazy. There's only 8 people in the competition and still 40,000 different ways that they could finish that competition. All right, let's say we're only concerned about those that finish first through third, like in the Olympics. Okay, we're only really concerned about those who get gold, silver, and bronze medals. In this case, there's only 3 spots that we're concerned about, first through third. Okay, there's 8 different people that could finish first. Once that person finishes first, there's only 7 that could finish second, and then 6 that could finish third. And then that's it. That's all that we're concerned about. We're not concerned about those other places. Okay, so in this case, there's 336 different ways that those 8 skiers could finish first through third. Now this, if you notice, is just a little section of 8 factorial. All right, and we're going to go on the next example and figure out why it's just that little section. All right, so from part B in example 4, an ordered group of 3 skiers is taken from the group of 8 skiers. This is a permutation of 8 objects taken 3 at a time. All right, that's also denoted as 8p3. What I like to say is the amount of permutations of 8 objects if you choose 3. Okay, so to calculate NPR, the amount of permutations of n objects, if we're choosing r, it's n factorial over n minus r factorial. Okay, so that would be in this previous case, 8 factorial over 8 minus 3 factorial. And if we do 8 minus 3 factorial, that's just 5 factorial. And if we write it out, okay, we can see why in the last example it was just 8 times 7 times 6. 8 factorial is the number of ways that all 8 of those people can finish. But if we're only concerned about those first three places, we don't have to consider those last 5 places. All right, so now let's use this. In example 5, you have 6 text messages on your cell phone, and let's figure out how many orders can you reply to 4 of the messages. All right, so in this case, we're assuming that order matters here, and we're taking 6 objects, and we're finding the number of permutations if we choose 4. All right, so 6p4, of course, we could write it out. That would be 6 factorial over 6 minus 4 factorial, which is 6 times 5 times 4 times 3 times 2 times 1 over 2 factorial, which is just 2 times 1. Obviously, the 2 and the 1 cancel out here, so we really just get 6 times 5 times 4 times 3, which is 360. Remember back in those buttons where I showed you how to use a factorial? In those same options, you can also type in 6p4. All right, you go to math, go to probability if you're on that TI-84 or TI-83 calculator, and you'll see the permutation option right there. It'll say NPR. All right, if you're on the TI-30XS calculator, it's pretty darn simple. You just hit that PRB button, which stands for probability, and then you go down to the option that has permutations. Now, we're still not done yet. It says now, what about if you want to reply to all 6 of the messages? All right, that would be like 6p6. So that's 6 factorial over 6 minus 6 factorial. If we simplify that, that's 6 factorial over 0 factorial. And remember, 0 factorial was just 1. So it's really just 6 factorial. If we type in 6 factorial, we get 720 different ways we could respond to all 6 of those messages. All right, now we're on to the last example. In example 6, your grocery shopping cart has 8 items, and how many orders can the checkout clerk scan 5 of those items? So in this case, we have 8 items to choose from, and we're choosing 5, and we're assuming that order matters. We're dealing with permutations here. So if we type that in, that is 6,720 different ways that they could just scan 5 out of those 8 items. And how many orders can the clerk scan all 8 of the items? Well, that would be 8p8 or 8 factorial, which would be 40,320 different ways. All right, if you like this, if you enjoyed it, if you found this helpful, please like, subscribe, and share. Thank you, and have a great day.